All right, fighting oxidative stress with oxidants. Obesity Explained, episode 6. This one is featuring superoxide production at complex 1. That's the bad kind of superoxide production. That is not the kind. We do not want to produce superoxide at complex 1 because it's associated with reductive stress, and we're going to get into that. And that little guy over there on the right, I'll explain all his features, but that is superoxide itself, which is superoxide is the root cause of oxidative stress when superoxide is produced in the cell, and we're going to see how to avoid doing that by using oxidants. And just a quick commercial note to help the blog: stearic acid is back. So a lot of people have been waiting for powdered stearic acid. It's been very hard for me to source since COVID, but it is back at fireinaBottle.net/shop, and I've got a new product, disodium succinate 800 milligram capsules. I've advertised the succinate before, but this is the first time that I've had disodium succinate in capsules. So check that out. So there's been a ton written about oxidative stress and its relationship to obesity. This is a paper where the abstract just simply starts off: obesity may be a state of chronic oxidative stress. So that's very strong language, implicating implicating oxidative stress, right, at the heart of obesity. And they have this big, scary looking arrow thing in there to show you how serious and scary it is. Here's another article. Obesity is associated with low grade, excuse me, I have a little cold, chronic systemic inflammation in adipose tissue. And it goes on: several chronic diseases are also the result of obesity, e.g., metabolic syndrome, diabetes mellitus, liver and cardiovascular diseases, and cancer, and associated with oxidative stress, right? They're very serious that obesity is causing oxidative stress, and oxidative stress is causing all of these other diseases, right? Here's yet another one. This is a Japanese paper: fat accumulation correlated with systemic oxidative stress in humans and mice. And they gave us this chart. This is T bars. T bars is basically measuring malondialdehyde, which is an oxidized polyunsaturated fat. So this is a measurement of oxidized PUFA, and that is the BMI on the bottom. So as people get heavier and heavier, have a higher and higher BMI, they have more oxidized PUFA, which is a symbol of oxidative stress. And just to be clear, right, T-bars, that's what they were talking about. T-bars is used to measure lipid peroxidation in cell and tissue extracts. That's oxidized PUFA, and this is according to abcam.com, which is a manufacturer of these kits that you use to test for oxidative stress. You're testing for oxidized PUFA. And so superoxide, where does it come from? Well, it's generated at the electron transport chain. And the electron transport chain is where we make our ATP from our food, and that is what drives our cells. And so you can see here, I've got NADH by the red arrow here. NADH is the NAD that carries the electrons, let's say. So NADH is the reduced form. It has the electrons, and we'll get to more about reduction and oxidation in a bit. And it dumps off the electrons, and it becomes NAD plus. And if you're wondering about the H, the proton, it just goes into solution. The electrons are transported through the electron transport chain, and 98% of the electrons follow this green arrow through the rest of the electron transport chain, and eventually they come over here and they make ATP. And that's how our body runs, is by shuttling these electrons that start with NADH, and they go through this chain and they come out as ATP over there. And that's really all you need to understand about it for the most part. But yet, I said 98% come through here, and 2% of them come out as superoxide. It's probably not really 2%. That number's probably high. On average, it might be less than 1%, but it's some non-zero number that is an important number. So what is superoxide? I've drawn all his features here. Obviously, he has a cool mohawk because he's a radical, right? He's a free radical, as they say. Um, he's got a cape because he's super, obviously. Um, he's made of dioxygen. So dioxygen is just the oxygen in the air, right? O2, dioxygen. And dioxygen, interesting molecule on its own right, but the difference between dioxygen and superoxide is that dioxygen has picked up an extra electron, which is to say that oxygen or superoxide is reduced oxygen. And again, we'll get to reduction and oxidation in a bit. Superoxide has this unpaired electron down here. So you can see all of these electrons are in pairs. And this one electron is there on its own. And that is what makes superoxide kind of reactive, because electrons like to be in pairs. So when you have this unpaired electron, it's looking around for a match. It's looking around for a mate, basically. It wants another electron. And oxygen itself is very electrophilic, which means it loves electrons, which means this superoxide is looking to grab another electron from somewhere to complete this electron pair. And that is where the problems with oxidative stress begin. And so, and in fact, superoxide itself is not that damaging in the cell. What actually happens down here is that, so the superoxide is typically converted to hydrogen peroxide by superoxide dismutase. And this reaction typically happens very efficiently. But some small percent, I've drawn 1 out of 1,000, that's probably not remotely accurate, but some very small amount of this hydrogen peroxide gets converted to something called OH minus or OH dot, and that is called the hydroxyl radical. And that thing is very reactive and does absolutely cause damage. This is the hydroxyl radical oxidizing PUFA. And so remember I said oxygen, especially oxygen with an unpaired electron, is very reactive. And oxygen wants to take electrons. Oxygen is always a taker of electrons in animals. And so the sort of easiest place in a cell that one can grab an electron is in a polyunsaturated fat, because this pair of double bonds, there's this kind of electron cloud, and it's very easy to yank electrons out of there. And so what happens is the hydroxyl radical just takes an electron from a molecule of polyunsaturated fat. So most likely that's going to be linoleic acid, which is typically the most common polyunsaturated fat that we see in most animals. And so so the OH dot is going to become H2O, so it's neutralized, it's now harmless. But in the process, this is a complicated reaction. But the end stage is we have this lipid peroxide. We have this oxidized PUFA that started initially with superoxide, and that is the problem. And again, the hydroxyl radical is an electron taker. That's important to remember. This is another view of that same process. This O2 dot minus, that's your superoxide. It becomes hydrogen peroxide. It becomes the hydroxyl radical. And that ultimately leads to lipid peroxidation of PUFAs. And that leads to the T-bars that we were talking about. That same kit that I showed to measure oxidative stress. And interestingly, antioxidants can step in here, and they can actually neutralize the hydroxyl radical and prevent that lipid peroxide or that lipid peroxidation and that T-bars from happening. And so antioxidants are electron donors. And so what's happening is an electron is moving from this antioxidant over to the hydroxyl radical. The hydroxyl radical can just grab a proton out of solution. It becomes water. And this whole problem of lipid peroxidation and T-bars is safely averted thanks to the antioxidant. Hooray. And so this is the reason why many studies have been done, given antioxidants to people, supplemental antioxidants in high doses, and saying this should cure cancer, this should or prevent cancer, this should prevent heart disease, perhaps this should prevent a lot of these problems. And so this is a part of the Cochrane library. They do these meta-analyses of all of these other studies, and these are considered very high quality meta-analyses. This one's called Antioxidant Supplements for Prevention of Mortality in Healthy Participants. So there's tons and tons of studies in this analysis. And what they conclude is that in the 56 trials with a low risk of bias, which is to say the best conducted 56 trials, the antioxidant supplements significantly increased mortality. Right? I didn't stutter. The antioxidant supplements significantly increase mortality. And so they don't work. Antioxidant supplements do not work as advertised. And if you're really astute, it's actually very clear why this is. It's not even that hard. I've talked a lot about how reductive stress leads to oxidative stress, and it kind of blows people's minds, and it's hard, and it was hard for me to even wrap my head around it first. But the more you think about it, you realize some very basic things, and then you're like, oh, well, that actually makes sense. We should have realized that all along, but we didn't. And so again, this is just the same slide as before. This is the beginning of the problem. NADH, the electrons from NADH are pinging back out of complex 1 to form superoxide. And some of those become hydroxyl radical and oxidize PUFA, right? That's the problem restated. And so where does the NADH come from? How does this all work? And so the food that we eat, fat, carbohydrates, ethanol, even some amino acids, all get converted into acetyl-CoA. Acetyl-CoA enters this thing called the Krebs cycle, also known as the TCA cycle. And essentially what happens is, and this is the heart of our metabolism, this Krebs cycle is at the heart of how we generate ATP. And there's these enzymes in there. This one is alpha-ketoglutarate dehydrogenase, but it doesn't matter. This Krebs cycle, what it does is essentially the energy in our food is held by these high energy electrons. And in the Krebs cycle, we transfer those electrons to NAD+, which is known as an electron carrier. And so this AKGD is giving the electrons to NAD+, which is the oxidized NAD, and it is becoming NADH, which is the reduced form of NADH. And you can remember this by the mnemonic oil rig, which means oxidation is losing electrons and reduction is gaining electrons. Okay, and so the NAD plus has given up its electron at complex 1, as we saw before in the mitochondria, and it's oxidized. And then it goes back to the Krebs cycle, and the Krebs cycle gives it another electron. Now it's reduced. It can go back to complex 1 and drop off that electron. And so this is a basketball analogy, as you can see. I apologize for the sports analogy, but it makes sense to me, so there you go. Anyway, so you've got our Krebs, and it's cycling over here. And as our food comes in, these electrons are being passed off to NADH. And then NADH has to run down to complex 1, so now it's in the mitochondria. And again, complex 1, that's when electrons go into complex 1. That's how we make ATP, the energy that moves our muscles around, etc. And so these electrons have to get transferred. And most of the time in a healthy cell, you've got a lot more NAD plus than you have of NADH. That's just how the system works. And so these NADH, it picks up the electron, runs down the court, makes a layup, and our ATP count goes up. Great, good for us. There's not even any real defense. Although having a lot of NAD plus around somewhat slows the rate at which NADH can run down the court and drop more electrons in. And the problem comes when too many of the NAD plus are actually carrying electrons, and they become NADH. I don't know if you've ever been at a basketball game. Maybe it's a kids practice, and they've got 10 basketballs on the court, and everybody's trying to shoot a layup at once. And what happens is sometimes those balls will collide in midair, and none of them go through the hoop. They all come pinging back out. And oxygen, molecular oxygen, is the Dennis Rodman of electron rebounding, if you will. Sorry if none of you watched the 90s Bulls or Pistons. But the take-home message here is that superoxide is reduced oxygen. So oxygen is there collecting all of the extra electrons that are rebounding out of complex 1 because there's too much NADH trying to shove electrons through it all at once. And that is the idea that there's too much NADH and not enough NAD+. That's the idea of reductive stress. It just means too many things are reduced. And again, because oil rig is oxidation is losing, reduction is gaining. So when too many NADH have electrons, they're all reduced. The cell's in reductive stress. Now they're all shooting at once. Electrons are pinging back out. Oxygen is grabbing those electrons. When oxygen gains an electron, it becomes reduced. So superoxide is reduced oxygen. That's confusing to people because they think about oxygen and they think about oxidized. This is from the Wikipedia definition of superoxide. This is in the first paragraph of the Wikipedia entry. The reactive oxygen ion superoxide is particularly important as the product of the 1 electron reduction of dioxygen O2. And so, yes, superoxide is reduced oxygen. So a buildup of superoxide is the thing that causes oxidative stress. Ultimately, it's the ultimate root cause of oxidative stress. Another way to say this, same sentence, a buildup of reduced oxygen causes oxidative stress. The electrons that reduce the oxygen come from the reduced form of NAD, NADH, right? And I know I'm being a bit repetitive, but I think this is tricky for some people, so I want to make sure that people get it. And so this is just to throw some more support behind this idea. This is an article about mitochondrial dynamics and superoxide production, and they do a bunch of experiments, and they conclude that the rate of hydrogen peroxide production was closely related to the level of NADH and NADPH reduction. So the more reduced the NADH pool is, or the NAD pool is, the more NADH and the less NAD+, the more hydrogen peroxide, which is an indicator of superoxide production, happens. And so in a highly reduced cell, it turns out you make more superoxide because the source of superoxide is all those electrons that NADH has. And so that brings us back to antioxidants again. What do antioxidants do? Well, they reduce things. A lot of modern diseases, I would argue, one of the root cause of the diseases is too much NADH and not enough NAD+. And I've provided a lot of evidence about this on my blog, and we'll see more evidence of that going forward. But I want to think about antioxidants and how they work. So I've said that antioxidants are electron donors. This is a classic antioxidant, curcumin. You probably all heard of it. It's a spice. I'm spacing on the actual name of the spice right now, but Google it, you'll find it. So curcumin has this. You can see this OH right here. That's how you eat it. And so they call it auto-oxidation in water, but the curcumin is gonna become oxidized when it's functioning as an antioxidant. It gives this electron up, and this electron comes off, and it becomes this other version of curcumin, which has this O dot. And so it's lost the electron, and that dot means now it has an unpaired electron. But the unique thing about antioxidants is the fact that it doesn't have this electron doesn't make it a free radical. This ring structure is super important. In most antioxidants, you'll see these ring structures. And what happens is when you have this ring of carbons, so they don't draw them in, but at every one of these angles here, there's a carbon atom. And, you know, technically in science class or in chemistry, you draw the orbitals where the electrons live like this. And so you think about it as the electrons belong to a specific carbon atom. But in reality, it functions more like this. You have this cloud of electrons shared between all those carbon atoms. So you've got like 12 electrons, and they're all shared in this cloud. And so they can actually, so the curcumin can actually give up one of those electrons. And now you have, you know, like 11 electrons shared between all the carbons. And so, forgive me if I got the numbers wrong. Maybe it's 6 and 5. I don't know. I'm not a chemist, but the point is that the way that those electrons are shared in a cloud means that it's okay for them to give up one. They'll live with it. And so, maybe you've already sensed the problem here. The problem with that, you know, when there's too much NADH, when there's too many electrons, we make more superoxide. And the curcumin, the antioxidant, is adding more electrons to the problem. It's like pouring water on a drowning man, right? And so this is a study that was done recently. It's a good study. They grew these cells in well, they did too. They did it in tissue culture. They also put tumor cells into a live mouse, and they gave them curcumin. And what they show is that in this hypoxic environment, which means it's low in oxygen, if you give the cells curcumin, if you give them this antioxidant, the NADH and the NADPH pools become very reduced. Because curcumin is shoving electrons onto the cell, and the cell deals with that by grabbing them up with NADH and NADPH. Oxygen is the terminal electron acceptor in biological systems. So if there's enough oxygen around, it's not that big a deal. So in normoxia, normal amount of oxygen, you kind of see this transient rise in NADH and NADPH. But if you remove some of that oxygen, you see this huge rise in NADH, because when you consume antioxidants, those electrons have to go somewhere. And if there's limited oxygen, if you don't have a terminal electron acceptor, that builds up as reductive stress. It builds up as NADH and NADPH. Again, this is that same study. Again, we already said this, but the rate of hydrogen peroxide production was closely related to the level of NADPH reduction. And as you can see, the antioxidants reduce the NADH and the NADPH. That is what they do, and that increases hydrogen peroxide production. And this other study shows that very well. So this is in a I believe a thyroid cancer tissue culture. And so they have these cancer cells growing, and they add curcumin to the medium, and you have this very rapid production of reactive oxygen species. So this is after 5 minutes. And you add the antioxidant. So now, right, in the previous example, there was no oxygen. And so all those electrons just built up in the NADH and NADPH pool. But if there's oxygen available, where do those electrons flow? They flow to create superoxide, because they just come surging in, and all you can do is hit that blow-off valve and turn them into reactive oxygen species. And so you see this case with with antioxidants, where they do have the ability to mop up some of those hydroxyl radicals, and they do absolutely have the ability to prevent some of that oxidative damage to PUFA and those lipid radicals, but at the same time, they're making the root of the problem worse, which is the fact that there's too much NADH and it's all trying to dump its electrons onto complex 1, and you're making more superoxide, right? So so the antioxidants are fixing a symptom of the problem, and at the same time they're making the root problem worse. And that's probably why people that you give antioxidant supplements to have a higher mortality rate, right? And this has been well studied, and there is significant mortality risk to taking an antioxidant supplement. And so this is the opposite case. And so if you've been watching the series, you know that I love talking about the aryl hydrocarbon receptor. It's a very interesting molecule, and in 1,000 ways. So the AHR, there's tons of evidence that an activated AHR causes obesity, and it's involved in 1,000 different pathways, and I've already hit on a bunch of them. We talked about, in I think it was episode 3, I talked about PARP, and PARP is an enzyme that breaks down NAD plus and it converts it to nicotinamide. And then in episode 4, I talked about NAMPT, which is downregulated by the aryl hydrocarbon receptor, and that recycles the nicotinamide back to where it can be NAD plus again. So the AHR is upregulating enzymes that break down NAD plus, and it's reducing enzymes that recycle NAD plus. And so the AHR in like 1,000 different ways is putting pressure on NAD plus levels in your cells. And so in this study, they gave TCDD to these cells, and actually I believe also to the live animals. And what you see is in the liver, you see this very kind of rapid, over 6 hours, you already have this significant drop in the amount of NAD plus that's available. And it continues, gets more dramatic at 24 hours and even up to 48 hours. The pool of NAD is becoming much more reduced over 48 hours in response to the AHR. It has more electrons, more of it is NADH. At the same time, so this is an older study, but this shows they gave rats a single dose of TCDD, which activates the aryl hydrocarbon receptor. And after 24 hours, after 1 day, I've got it underlined in red. This is T-bars again. That's what they're measuring here. And so they're measuring those oxidized PUFA, and they go from 100% of controls up to about 130% of controls in 1 day. And by day 3 or so, the oxidized PUFA have doubled, and by day, 4.5, you literally have almost 5 times the amount of oxidized PUFA in response to TCDD, because that NAD pool is more reduced. This is another one. This is liver superoxide production. They were looking at actual enzyme rates in this study, and they showed that the more TCD they add, the more reduced the NAD pool gets, the more superoxide is produced. So reduced things cause superoxide, because superoxide is reduced oxygen. And so then there's this other tool that is used in tons of experiments, and it's called alpha lipoic acid. And alpha lipoic acid is actually a really good supplement. I sell it. I also sell this on fireinabottle.net. The biggest complaint I've heard about it, by the way, when people try to take it, is like kind of and I've experienced the same thing, a little bit of like a fatigue and like a head swimmy thing. There's another version of it called R alpha lipoic acid, which anecdotally people have told me they've had better luck with in terms of not getting that immediate fatigue from taking it. If you want to try some, but I also have the normal ALA on the blog that most people take. And so ALA is a really interesting thing. If you look at the medical literature, they repeatedly refer to it as an antioxidant. If we go by that classic definition of antioxidants are electron donors, ALA is the opposite of that. It is an electron taker. So when you consume ALA, it gets taken into your cells, and NADH, it converts NADH to NAD plus. So the NADH pool gets oxidized. So the ALA is doing the exact opposite thing of TCDD and an activated ARA hydrocarbon receptor. And what happens is the ALA gets converted to this dihydro lipoic acid, and it just gets broken down and excreted. And ALA is a natural compound that our bodies make, and so the cells see it and they transport it in fairly rapidly, and it fairly rapidly reduces your NADH pool, and like you say, and then you just get rid of it. And so in this study, they showed that. So this is the NAD to NADH ratio. And so this is the thing that went down when you treated the animals with TCDD and activate the AHR. And in these animals, when you when you give them ALA, the exact opposite thing happens. That NADH pool becomes oxidized, and you see this tripling in this case of NAD plus levels. And what they showed in that study is that these mice were made obese through this kind of complicated method, and on the high dose ALA, those mice basically are as lean as normal control mice. Despite the fact that these mice start off diabetic, but you take these obese diabetic mice, you give them ALA, you oxidize the NAD pool, and the mice are lean. Also, here's another effect. The effect of alpha lipoic acid on lipid peroxidation. So this is another one. They took diabetic rats. They gave them ALA, and you have this huge drop in T-bars, right? Again, so you have a significant drop in oxidized PUFA as a result of treating these diabetic rats with alpha lipoic acid. And so my alternative hypothesis is that reductive stress, which is to say a highly reduced NADH pool, is the root cause of both obesity and oxidative stress. It's not to say that obesity and oxidative stress aren't correlated. It's just that those early studies that I mentioned have the causality wrong. The root cause is reductive stress. Those extra electrons are causing both the obesity and they're causing the oxidative stress. And so this is a really interesting paper. It's one of my favorites. They took these mice. So one of the things that TCDD does is if you give it to mothers, it causes birth defects. And so they give TCDD to these mice, and the mice have under the baby mice, they don't fully form their genitals. They have all these problems with their steroid hormones and their sex hormones. And the interesting thing, and so what they find is that TCDD, all of the damage done by TCDD was totally reversed by alpha lipoic acid. If you gave these mice TCDD plus alpha lipoic acid, the development of the fetuses were fine. They had normal amounts of steroid hormones. They grew normal testes. And so the ALA, by reducing the by oxidizing the NAD pool, completely fixes all of the problems caused by the TCDD. And because, like I say, a lot of what the ARA hydrocarbon receptor is doing is it's just affecting the NAD plus to NADH ratio, which is this ancient signal that's a 3 billion year old evolutionary signal for what cells should do. And the AHR is just messing with that, and you can fix it somewhat with alpha lipoic acid. The reason I love the study so much is not necessarily that, but they found that while lipoic acid also acts as an antioxidant, the other antioxidants failed to exhibit any beneficial effects. And here's a graph of that. And so in a normal mouse, this star is involved in steroid hormone production, and converting cholesterol into steroid hormones. You can see in a normal mouse they have 100% of the star mRNA is produced. If you give them TCDD, that level goes down to about half of what it should be. Let's jump over here quick. These three things are classic electron donor type antioxidants. BHA is in a lot of food labels. It keeps the fats from oxidizing in your food. Has zero effect. You still have these guys wound up with 50% of the control levels of star. EDA, this is another control column. EDA is maybe even worse. Vitamin C, no benefit at all. So they tried these three classic antioxidants. They all fail. Lipoic acid, it completely reverses the problems caused by the TCDD. The star mRNA is exactly what it should be, because lipoic acid is an electron taker and it's oxidizing the NAD pool, and you need an oxidized NAD pool. Lastly, so I love to have relevant human examples, right? The rodent studies are great and it teaches us about the fundamentals, but CYP1A1 is an aryl hydrocarbon receptor target gene. And so this is a 2022 paper about this drug called Clozapine. And unfortunately, a lot of people have to take Clozapine. It's given to people with schizophrenia who the first line treatments against schizophrenia don't work. And Clozapine has good effects towards helping with some of the symptoms of schizophrenia, but it's been known for a long time. This is an old drug. They don't even really know exactly how it works. But it's been known for a long time that Clozapine causes weight gain in a lot of people. And this is actually a 2022 paper. So this is very recent. And what they showed was that Clozapine activates the aryl hydrocarbon receptor. It works a lot like TCDD does. And so it's not nearly as potent as TCDD, but nonetheless, Clozapine is activating this aryl hydrocarbon receptor target gene in a dose and time dependent fashion. And this suggests that Clozapine, in fact, acts like TCDD does to activate the AHR. This study is about the amount of weight gain and diabetes caused by Clozapine. This first one is weight gain, and this red is the average. And it's an interesting chart. Everyone starts at 0, and then this axis is how much weight is either lost or gained. So you can see that actually some people lose weight on Clozapine, and that's not totally shocking, because the whole reason that we found out about the aryl hydrocarbon receptor is that TCDD actually causes a wasting syndrome in some people. And so activating the AHR has all kinds of effects on your metabolism, and in a lot of people it causes significant obesity. Some people it causes wasting syndrome. And so after people take this this Clozapine and activate the AHR, their weights are all over the place. But on average, you see significant weight gain, and this is over a period of 60 months. And so the weight gain continues to pretty much increase through about 4 years, and then it kind of levels off. And the average weight gain is around 20 pounds or a little more, but there's a significant people who gain 50 pounds or more on the Clozapine. What's more shocking is this graph on the right. So these people start off at 0% of them are diabetic. These are mostly young people in their 20s, maybe 30s when schizophrenia sets in. And within 5 years, nearly 40% of them have full-blown diagnosed type 2 diabetes. So this Clozapine is one of the most effective, if not the most effective, diabetes-causing agent that is perhaps ever been used in humans. I don't know. And so they do a lot of tests to see, well, is there a way that we can prevent some of this weight gain caused by Clozapine. And so this was a test of alpha lipoic acid, right? Because if we can oxidize that NADH pool, we can perhaps prevent some of the weight gain. And so it's in a small group of people. This is only 7 people. You can see they're mostly young. They're mostly in their late 20s to 39 is the oldest person. And this is the drugs that they've been taking. Most of them, 5 of them have been taking Clozapine. The other ones have been taking this related gene risperidone, which when I look at it, to my eye, it's got a couple rings, which is the ARA part of the hydrocarbon receptor, and it's attached to fluorine, which is the type of thing that would activate the AHR. And so it's a very similar drug, and I suspect it's doing a lot of similar things. This is how long they've been diagnosed with schizophrenia, and so some of them. Oh wait, no, I'm sorry. This is how long they've been taking their current medication, the Clozapine. I cut out that other column; it wasn't that useful. Anyway, so and this is how much weight they've gained: 25 kilograms. So that's close to 60 pounds on average. These patients have gotten, and some of them, like this subject FF, is a 37-year-old female. She's been on Clozapine for 4 months. And she's gained 31.8 kilograms, which is almost 70 pounds in 4 months on Clozapine. And a lot of these people, 4 months, 7 months, 27 months, 20 months, these are people that, in that previous graph, the Clozapine should still be causing weight gain, right? The Clozapine caused weight gain up to about 48 months of treatment. And so these people should still be rising in weight. They gave them alpha lipoic acid, and over 12 weeks, you have this fairly steady and somewhat dramatic drop in weight. So that's 3 kilograms in 12 weeks. That's about 7 pounds. Just by, they're still taking the Clozapine, but now you give them the ALA, you oxidize that NAD pool, and some of that weight gain starts to be reversed. This is another report in the literature. This is a case study. So case studies are just like where doctors write down a bunch of N equals 1. This patient came in, I did this happened. And doctors report that because it's useful to other doctors to see, what has been tried, what might have worked, what are ideas I can come up with. And so it says a 26-year-old man had been receiving Clozapine for 27 months. He gained 29.4 kilograms. Again, that's 65 pounds or something. After 12 weeks of thioctic acid treatment, and thioctic acid is just another name for alpha lipoic acid, he had lost almost 9 kilograms and reported appetite loss and increased energy. He continued to receive the ALA and lost a further 16.4 kilograms over 9 months. So that is a loss of about 25 kilograms. So he gained 65 kilograms on Clozapine and then lost 55 kilograms of it with Clozapine and ALA. And so anyway, that brings us to the end of this one. Conclusions: antioxidants are electron donors. Antioxidants reduce the NAD pool. Antioxidants convert NAD to NADH. The reduced NAD pool, there's a lot of NADH, that drives superoxide production at complex 1. The AHR also reduces the NAD pool. So the ARA hydrocarbon receptor and antioxidants in some ways work in a very similar way. Their mechanisms are very different, but both of them can wind up with a highly reduced NAD pool. Alpha lipoic acid acts in the opposite way to antioxidants and to ARA hydrocarbon receptor activation. It oxidizes the NAD pool. It converts NADH back to NAD+. And the effects of alpha lipoic acid counter the activation of the aryl hydrocarbon receptor. And so that's all great. I hope that made sense. I know that's a lot of science. And people who follow my blog might say like, oh, but you always say superoxide production is a good thing. And it often is. And we're going to talk about that in the next episode. We're going to talk about when and more importantly, really where superoxide generation is good and where superoxide generation is bad. And I kind of already told you it's bad when you make it at complex 1, but it's good when you make it at complex 2, and it's good when you make it at pyruvate dehydrogenase. And we're going to talk about that in the next episode, and we're going to talk about the disodium succinate that I'm offering on the blog and how that helps drive ROS generation at complex 2, and how great that actually is, even though I just said driving superoxide has problems and creates oxidative stress. And so, context is crucial to determining the effects of superoxide production and whether they're going to be good and whether they're going to be bad. And a lot of this depends on, are you in reductive stress when you produce the superoxide? And we're going to look at the details of why being in reductive stress and producing superoxide is bad, and being out of reductive stress and producing superoxide is good. So check back in.